Here we are, kids. Last lesson of chapter 7. I do feel like this chapter is all out of order, but it doesn't matter. We're at the end. We're just going to kind of meld it all together here. So this is using linear models to interpolate and extrapolate. And we'll talk about what those mean in a couple minutes using some real data. So using what you know about writing equations in slope-intercept from graphs or from data can help you make informed decisions about the future, or can help you find, for example, unknown data. So that's what we're going to do. We are going to use tuition for public schools from the 90s because the tuition for schools now is just depressing. And this is the data that I had, so this is what we're going to use because it fits nicely in our example. So here we go. We are going to first take this data and fit it the best that we can onto a coordinate plane. And so you'll notice that I started with 1990. Now, would it be intelligent for me to start at 0 and go all the way up to 1990? No, that would be crazy town. So we are not going to do that. So that is why, back up, typically the left column is the x and the y column is the right. Okay, so that's why I'm going to start at 90, 91, 92, 93, if you want to write them all in, 95, 96, 97. This is when I learned how to drive a car. That's how old this data is. That's when I graduated from high school. You guys weren't even thought of, and so forth, right? It's kind of fun. This is a vintage math problem. Vintage is trendy. And then we have our money. Now the money, again, starts at a high value, so I'm not going to start at 0, and it does not increase by 1 like our years did. So we need to find a suitable, dollar amount to assign for each box. So I am ranging from 2,000 to 3,100, so about what, 1,100 or 1,100-ish, and I have 12 boxes, so I think it would be reasonable to number up by 200s. We're going to have a little space left over, but that's okay. So 2,400, I had this set up for you. You, of course, could do this on your own, but it takes a little bit of time and thinking, and I didn't think you'd want to sit here and watch me think for a large amount of time. Okay, so now we have the coordinate plane that we're going to use. And now we can plot our data that's available to us. So in 1990, college was just over $2,000. I'm going to have to estimate some of these, right? In 91, it says 2,159. There's 2,100, so right about there. 92 was just over 2,400. 23 is unknown, so I'm just going to skip it. 94, 28, 20. Right about there. And 95 was just under 3,000. And 96 was 3,100. Right there. Okay. So that's my data. Now, does this look linear? It does to me. Yes, it doesn't go up and down and all over the place. Okay, so now I'm going to draw my line of fit. Yours might be a little bit different than mine. It's subjective, but it's not, remember, it's not connecting the first and the last points. And I like to extend my line from one side of the coordinate plane to the other, to infinity and beyond. Okay. All right, and so now we can write an equation. We can either just look at the thing and write our equation from there, or you can use 2 points. Now here's my problem. So here, see how it goes up one, right one, up one, right one, up one, right one, up one. So I'm tempted to say y equals x, but remember each of these x's represents 200, so it'd be y equals 200x. But if I keep doing that, it doesn't go through, it's not quite 200. So it depends on how accurate I want this to be. I could, if this needs to be very accurate, use 2 points and calculate the slope. So call this y1, y2, x1, x2. I could do 3,151 minus 2,977 over 1,996 minus 1995. Well, the denominator is easy. 1. For Pete's sake. 4, 7. So 174 in that year, but that would just be comparing these two. Remember when we're writing an equation, we should use 2 points that are far away from each other. So I probably should have used 1996 and 1990. Okay, and so I could calculate slope that way too, and it's going to come out to be about 200 as well. I think it comes out to be 193 actually. So you can use what you want. I'm going to say for this example, y equals 200x, knowing that it's going to be a smidge off because it doesn't come out perfectly. And then my intercept was 20, well, I started at 2035. It's not necessarily because that's where I started, but that's where my line of fit goes. Now, could you use this data and calculate an intercept and use it that way? Yes, you could absolutely do that too. Okay, so it just depends on how precise you need this to be. So basically what that means is since 1990, off of a base of $2,000-ish, there's an increase about $200 every year. Now, why do we care? Well, you can use this to interpolate, so find, estimate numbers within existing data. So if this bugged you and you wanted to find this unknown, you could either mathematically find or use your coordinate plane to find points between existing data. So this looks about 2,600. You can use a squiggle and a $sign. And then we can estimate points behind. So this would have been good for me when I graduated in 99. I might want to know how much college would cost in 2000. So I can extrapolate, find data beyond where we have the existing data. So this is 3,200, 34, 36, 38, about 3,900 for me. I don't even want to think about what it is for you kids because I'm going to have to put a kid through college too. So that's just a, I don't know, cool lesson that you can use to make good predictions. Remember, we do our best. These aren't the best lessons. Another teacher might do it a different way, but my main point for you guys is to know these two terms, interpolate and extrapolate, to look at situations and know how precise you need them to be, if estimating is good enough, or if you need to be more precise, and yeah, to know how to make a coordinate plane where you have to adjust, or a graph where you have to adjust values so that it fits on a coordinate plane. So that's that. We are going to do just a little bit of homework. This one's not bad. Okay, so this top section is kind of a throwback to section 5.4. just determine if this looks like a linear model or not. Does the data look like it's making a line or not? So you can give me a yes or no in the top. Question number 7 is telling you to tell me the difference between these. Another train. I don't know if you guys can hear the trains on the recording. They have a tendency to come by when I am recording videos. Explain the difference between interpolation and extrapolation. You can use your notes to help you with that. And you can, this is kind of a challenge question, tell me how to decide whether a data set can be represented by a linear model or not. How can you determine if it's linear or not? Okay. I do want you to do these next 2 questions because I feel like they're very important. It says, using this equation, represent the amount of money in dollars in your savings account, old numbers again, but 1988 to 1998. And so X is going to represent the number of years since 1988. So, for example, if we're looking for 1992, how long has that been since 1988? Yeah, that's 4 years. So because of that, you are going to put then 4 in for X and then continue to solve. I don't want to do too much for you, okay? So that's interpolating, finding data within, because 92 is between 88 and 98, and then extrapolate to find your savings beyond this if you continue to save at that rate. Okay, here is another equation for the cost of going to see a movie. And so again, your baseline is going to be 1985. So we're going to interpolate because we're going to look at 1991, which is between 1985 and 1995. So it was 6 years from 1985. So your X is going to be 6. But you do the rest, then use extrapolation to find 1997 because 1997 is beyond 1995. So, I think you should get this. If not, please don't hesitate to shoot me an email. Always happy to help. Or you can find me in class or before school. Thanks, guys, and I'll catch you later. Bye.